Having considered the hypergeometric theory in the last video, and we also saw that many of the special functions we consider like Bessel, Legendre, Laguerre, and the rest of them, they are special cases of the hypergeometric function. So it's important to look at this particular episode, which is about the unified theory of special functions. So it feels like the hypergeometric theory unifies all of them. So Unified theory of special functions. This lesson develops a unified framework for understanding hypergeometric functions, Bessel functions, Legendre functions, Hermite functions, Meijer G functions, and Fox H functions. Many classical special functions are actually special cases of generalized hypergeometric structures. So let's again remind ourselves of hypergeometric functions, which we considered in the last video. So the ordinary hypergeometric function is defined by sub 2 f sub 1 of a comma b sub semicolon c semicolon z. Now z is the variable. In the other video we used x, so anyone you use, just be sure which one you're focusing on. So and that is equal to summation from n equals 0 to infinity per comma a sub n per comma b sub n over per comma c sub n z raised power n over n factorial. So if it was x, we'd have had x raised power n like that. So where the per comma symbol is per comma a sub n, which is equal to a into a plus 1 into a plus 2, all the way to a plus n minus 1, with a sub 0 equals 1. So the function satisfies the hypergeometric differential equation given as x into 1 minus x, y prime prime plus c, into a plus b plus 1, x, multiplied by y prime minus ab. Oh, sorry, this is x, right? Y prime minus aby equals 0. Of course, I just use x in the place of y in case we're using x. So in the last video, we used x. So it's just everywhere we used x, it just becomes z. So no big deal. So this equation serves as the foundation for many classical special functions. So this is more like the foundation for many special functions that we get to consider. So all the other special functions would just be like maybe some modifications to this particular hypergeometric equation. Okay, so then we talk about the generalized hypergeometric functions. The generalized hypergeometric function sub p f sub q into a1 all the way to ap, b1 all the way to bq with variable z is simply summation from n equals 0 to infinity per comma a1 sub n all the way to per comma ap sub n all over per comma b1 sub n all the way to per comma bq sub n multiplied by z raised power n factorial. So that's a generalized hypergeometric function. So important special cases of this will now include the exponential function. The exponential function happens when p is 0 and q is also 0, right? So in that case, you just have only summation for, because all these things, this everything here will just evaluate to 1. So you just have summation from n equals 0 to infinity for z raised power 0 over, z raised power n over n factorial, because p and q are 0 in that situation. So that'll be e raised power z simply. You have Bessel. So exponential is 0 f0. Bessel is 0 f1. Hermite is 1 f1. And Legendre is 2 f1, right? So you have exponential 0 f0, Bessel 0 f1, Hermite 1 f1, and Legendre is 2 f1, like that. And then we move on to see hypergeometric function. We did this in the last video. Um, you know, so with variable z being 0.5 or whatever you want to assign to it, and then you just a is 1, b is 1, c is 2, and then you can do this and get the value. So you can print the value of this, which is 1.38629436111198901, like that. So that's the hypergeometric function if you want to compute it using SciPy and non-pi. Okay, so with that in place then, so we know Bessel is 0 f1. So for Bessel now, you have the Bessel differential equation. So you see, this is just like a modification of the original thing. So this is x squared y prime prime, of which this one here is z minus 1z. So it feels like here now that um you have z squared. So somehow, this is z times z multiplied by y prime prime. And then for the y prime, instead of having all of that plenty thing, you just have xy prime, right? just have xy prime, or if you like, yeah, xy prime plus x squared minus nu squared y equals 0. So its solution, the solution to this one is now the Bessel function. I've made videos on Bessel theory already and its applications. Then you then have the hypergeometric representation of this to be j sub nu of x equals x over 2 raised power nu all over gamma nu plus 1, 0 f1 into all of this, semicolon nu plus 1 semicolon minus x squared over 4. Those Bessel functions are special cases of confluent hypergeometric functions. So an example of that would be this. If you take nu to be 0, that means that j sub 0 of x will be sub 0 f sub 1 in of semicolon 1 semicolon minus x squared over 4. So if you use the series expansion, so you have this now to be equal to summation from n equals 0 to infinity of z raised power n all over n factorial squared. N factorial squared. So then we obtain, we now obtain that this is minus 1 raised power n over n factorial all squared into x over 2 raised power 2 raised power n. So that'll be the expression we get in that case in terms of hypergeometric expressions. So for the Bessel function, then we can evaluate it. In this case, we need I of OF1, that's Bessel, and then we need J naught to compare the direct Bessel and the hypergeometric type of it. So if we run this now, we get this. So you see, they're basically the same. If you use direct Bessel is the one with J sub 0, which we get also from SciPy special, and the Bessel using hypergeometric is now hype 0f1, like we saw already. So they are basically the same thing. Then you have the Legendre function as hypergeometric function. So Legendre's differential equation is 1 minus x squared y prime prime. So you see there's a modification now. Minus 2xy prime plus n into n plus 1 y equals 0. So the Legendre polynomial has a hypergeometric representation. P sub n of x equals sub 2f sub 1 into minus n comma n plus 1 semicolon 1 semicolon 1 minus x over 2. That's the difference in this case. So a very good example of that would be using P2 of x, which is 2f sub 2f sub 1 into minus 2 comma 3 semicolon 1 semicolon 1 minus x over 2. The series terminates because of the negative parameter. So because of this negative parameter, now the series terminates at order 2. So after simplification, you just end up getting P2 of x, which is a classical second order Bessel, So you have 1 over 2, 3x squared minus 1. So if you check under Bessel, we did exactly this kind of thing at some point. So if you do the direct Bessel, or you do yeah, we are talking about Legendre, not Bessel, sorry. So this P2 of x is second order for Legendre, not Bessel, sorry. So yeah, so you get hype 2f1, which is Legendre from SciPy special, and then you can get the evaluation of your Legendre directly. And they're exactly about the same. Then we have the Hermite functions as hypergeometric functions. So don't forget the underlying thing is that, we're talking about the unified theory of special functions, and we have seen it that the hypergeometric function is more like the overarching function representing all of them. And each of the other special functions is just a variant, a special case of the hypergeometric functions. When you just tweak some parameters. So the Hermite equation is y prime prime minus 2xy prime plus 2ny equals 0. So in this case now, you have nothing, everything in front of y prime is now like 1, and all that. So for indices, you have h sub 2n of x equals minus 1 raised power n, 2n factorial over n factorial, 1f1 into minus n semicolon half semicolon x squared. So for even indices, that's what happens. For odd indices, you have h sub 2n plus 1 of x equals minus 1 raised power n, 2n plus 1 factorial over n plus 1 factorial. So this is the difference here. And then in addition to that, you now have 2x, then 1f1 minus n 3 over 2x squared. So a very good example is the Hermitian 2, that's minus h2 of x. So using h2 of x, which is, this is even now. So you have, minus 1 raised power 2. That'll make this part positive. Yep. Yeah, so you have minus 2, 1f1 into minus 1, half x squared. So with all that in place, since 1f1 of this will be 1 minus 2x squared, then we can obtain h2 of x to be 4x squared minus 2. That's like 2 into 2x squared minus 1. And that's what Hermitian really looks like. So we can evaluate the direct Hermitian and of course the one based on hypergeometry, and you see everything just gives you 2 in this case when x is equal to 1.0 for those same parameters. Then we talk about the confluent hypergeometric functions. The confluent hypergeometric equation z y prime prime plus b minus z y prime minus ay is 0. Its solution is 1f1 a semicolon b semicolon z. So many special functions arise from confluent hypergeometric structures. So you have functions like, and their representation, you have the Hermite, which is 1f1 Legendre, 1f1 Bessel, 0f1 hypergeometric, and you have the Airy, which is the limiting case. Those are some special functions which arise from confluent hypergeometric structures. Then we have the major G functions. So for the major G functions, right? The major G function is defined by the Mellin-Barnes integral, which is G sub P comma Q super M comma N into Z slash A11 to AP, B1, A1 to AP, B1 to BQ. And you have this is equal to 1 over 2 pi I integral along L for this whole expression like that. So the major function unifies exponential functions, Bessel functions, hypergeometric functions, logarithmic functions, and trigonometric functions. So in one place, you have everything put together: exponential, Bessel, hypergeometric, logarithmic, and of course, trigonometric functions. So examples of major functions are you have the exponential function, which may be written as e raised to minus x, that is g sub 0, comma 1 super 1, comma 0 into x, uh, you know, that by minus 0. So the Bessel function will be written as j sub nu of x equals g sub 0, comma 2 super 1, comma 0 into x squared over 4 given minus of the v nu over 2, comma minus nu over 2. So these are some examples of major functions. So you can then import from simple you can import major G, and from simple you can import symbols, and then you can have your expression major, all of this, and then you have this. So if you put values in here, you can of course always get them back. So let's say if you have 1 minus 3 4, I'm just putting this, let's see what happens. So okay, that isn't working because it says no parameter A1 and may differ from any B1. Okay, I get it. So probably I have some values that are not meant to be. So let me just do this. If not, just keep moving. Okay. Yeah. So let's leave it the way it was. So for major G, this is what we get. Then we talk about the Mellin transform connection. The Mellin transform, which is M of f of s, which is integral from 0 to infinity, x raised by s minus 1, f of x dx. Major G functions naturally arise when Mellin transforms produce products of gamma functions. So this makes them useful in asymptotic analysis, statistical mechanics, fractional calculus, and wireless communication theory. Then we go on to talk about the Fox H functions. Fox H functions generalize the major G functions, and they are defined by H sub P comma Q super M comma N into Z given A1 small AI to big AI, then small bj to big bj. So the gamma functions now contain scaling factors. You have gamma AI plus gamma small AI plus big AI multiplied by S instead of gamma A sub I plus S. So for Fox H functions appear naturally in fractional differential equations, Levi distributions, anomalous diffusion, fractal systems, and stable probability laws. Then we go on to talk about the hierarchy of generality. So the hierarchy is you have elementary functions. We already said that elementary functions are functions like um, elementary functions are functions that are not special, and they include both polynomials and transcendental functions. So polynomials are things like your normal linear polynomials, linear expressions, right? Quadratic expression, cubic expressions, and so on and so forth. While transcendental functions are functions like sine, trig functions, inverse trig, exponential, logarithmic, and all of that. So the hierarchy of generality, now since we're talking about the unified theory of special functions, so you have elementary functions which are subset of hypergeometric functions, which are subset of Meijer G functions, which are subset of Fox H functions, because we know for Fox H functions generalize the Meijer G functions. So this forms the modern unified theory of special functions, and that is the summary of everything this video is about. So talking about the unified differential equation perspective now, many classical equations reduce to hypergeometric equations, like Bessel. Bessel can reduce to confluence hypergeometric. Legendre can reduce to Gauss hypergeometric. Hermite can reduce to confluence hypergeometric. Legendre can be reduced to confluence hypergeometric. Jacobi can become hypergeometric, and Gegenbauer can become hypergeometric. So thus, hypergeometric theory provides a universal framework for special functions. So we talk about representation theory perspective now. Many special functions are connected to symmetric groups. So I mean, we are going algebra now. Because representation theory is about algebra. So you have Legendre, like SO3, Hermite, you have the Heisenberg group, and Bessel. The symmetric group connected to Bessel is Euclidean group. So the symmetric group connected to Legendre is SO of 3. Hermite, you have the Heisenberg group, and Bessel Euclidean group. This provides a deep mathematical interpretation of special functions. So we have summary then. The theory of special functions forms a nested hierarchy where you have elementary leading to the generalized hypergeometric, leading to Meijer G functions, and leading to Fox H functions, which generalize Meijer G functions. So the key ideas are as follows. Classical functions are hypergeometric in nature. Then Meijer G functions unify Mellin transform structures. Fox H functions generalize Meijer G functions. Fractional calculus naturally leads to Fox H functions, and symmetry theory provides a deeper interpretation. Thus, many apparently unrelated special functions are manifestations of a few universal analytic structures. Then we come to our practice problems. So you have the hypergeometric functions. You want to show that 0f 0 sub 0f sub 0 of z is simply the same thing um, as e raised power z. I mean, we've seen that a lot, talking about everything we've been doing here so far. So then, yeah, I'll just flash the questions and then we start taking them one after. I'm going to solve problem 6 and 17. Problem 6 and 17. So these are, you have 1, 2, 3 here. Problems 1 to 4. Yeah, 1 to 4 more or less. Then you have, yeah, Bessel. You have them in 5, 6, 7, 8. You have Legendre. So I'm solving 6, right? So we're taking care of questions. You want to prove that j minus half of x is equal to square root of 2 over pi x cos x using hypergeometric or gamma function identities. So that's the first thing we're doing there. And then, okay, we have Legendre functions dealing from problems 9 to 12. Of course, we've done something with this Rodrigues formula stuff before. Then we have the Hermite functions. So, and for the Hermite functions, we are dealing with the last problem. Uh, that's problem 17. No, not that we are not taking 16, sorry. I'll be taking 17, which is about major functions. We want to show that the Mellin transform of e raised to minus x is gamma s. And explain why this leads naturally to Meijer G representation. Then problem 18 talks about using SymPy to compute a symbolic Meijer G function and simplify the rest. And you have the Fox H functions now in 19 and 20. So we're solving problems 6 and 17. So we're dealing with problem 6 here, to prove that all of j minus half of x is all that, and we're dealing with 17. Show that the Mellin transform of e raised to minus x is gamma of s and all that. So let's go on to problem 6 now. So problem 6. So we want to prove that j minus half of x is equal to square root of 2 over pi x cos x using hypergeometric, or gamma function identities. Okay, So solution. So we start with this. That's a Bessel expression right there. So we say the Bessel function has the series representation, has a series representation. J nu of x equals summation from n equals 0 to infinity. In case you don't know much about Bessel functions, you want to revisit there are two videos on Bessel functions. The first one is Bessel theory, and then the other one is application. So it's still in this playlist. So you want to check that out. So you have gamma n plus nu plus 1, then all multiplied by x over 2 is by 2n plus nu. Okay, so we have that. So here now, because we need j minus half of x, that means that this nu is automatically minus 1 over 2. So we can set that. So set nu to be minus 1 over 2. So if nu is minus 1 over 2, then it means that then we have j minus half of x. To be anywhere you see nu, you just put minus half. So summation from n equals 0 to infinity minus 1 raised power n, then n factorial, then uh gamma. So gamma, right? N plus nu plus 1. So that's gamma n minus half plus 1. That's gamma n plus half, basically. And then you have x all over 2, then 2n plus v. 2n plus nu. Nu is now minus half. You have 2n plus nu here, but nu is minus half. So we have 2n raised by minus half. So with this now, we have taken that first step. So the next thing is we can factor out the common power. Factor out the common power. So if you factor out the common power, we see that we have x over 2 raised by minus, there's still n under this place. So we can break this up into x over 2 raised by 2n, then x over 2 raised by minus half. So we can bring out the minus half and then leave all the other things at the other side there, like that. Okay, so to do that, we then have j minus half of x equals x raised by minus 1 over 2. I mean, x over 2 raised by minus 1 over 2. Then summation from n equals 0 to infinity for minus 1 raised by n all over n factorial gamma n plus 1 over 2. Then, x over 2 raised by 2n, you can take the power inside. That's like x squared over 4 raised by n. So this 2 just goes inside. So we can write it that way. So this is x squared all over 4 raised by n out there. So we can then we can now use the gamma, use the gamma function identity. Use the gamma function identity. So if we do that, we have gamma n plus half, right? We have gamma n plus half here. So we know that gamma. Okay, I think I'll just keep going, right? Okay, let's do this separately. So we know that gamma n plus 1 over 2 is gamma n plus 1 over 2 would have to be 2n 2n factorial all over 4 raised by n factorial square root of pi. So we have that. So in that case, we have another n factorial down there normally. So also in the denominator, we know we have we have 1 over n factorial gamma n plus 1 over 2. So that means we have 1 over n factorial times 2 raised by 2n factorial up here. Okay, no, this is 2n factorial. So this will be 2n factorial 4 raised by n factorial, then root pi. So this is root pi up here. So if we tidy all of that up, this cancels this. So we then have 4 raised by n goes up. So we have 4 raised by n all over 2n all factorial square root of pi. So with all of that in place, then, we have taken care of, this whole part. So we just put it back there and keep moving. So we can say hence j minus half of x is now x over 2 raised by minus 1 over 2, then multiplied by, we have this 1 over root pi can come, 1 over root pi will be here, then summation from n equals 0 to infinity for, minus 1 raised by n, then x raised by 2n, this x squared raised by n, that's x raised by 2n. Then down here, we have 2n factorial, 2n all factorial. Okay, trying to see that 4 raised by n. Yeah, the 4 raised by n here, um, the 4 raised by n here will automatically cancel the 4 raised by n down here. So that 4 raised by n that is coming from here will cancel this. So this is what we are left with by the time all of that is done. So we have this. So from here now, we can see that this is looking like cos x. So we can recognize the cosine series. Recognize the cosine series. The cosine series can be given as cos x equals summation from n equals 0 to infinity minus 1 raised by n, x raised by 2n, all over 2n all factorial. Therefore, we can say that j sub minus half of x is x over 2 raised by minus 1 over 2. Then all of that multiplied by 1 over root pi times cos x times cos x. Of course, we can simplify this. That means we have j raised by minus half of x equals, of course, this will be 2 over x raised by half. And this is 1 over root pi times cos x. So that is j sub half of x equals square root of 2 over x, because raised by half is that. Then you have 1 over square root of pi multiplied by cos x. So because this one also already has a square root, so we can put everything together. So that's root 2 all over, that's root 2 all over pi x times, that's multiplied by cos x. And this proves the identity we are looking for. J sub minus half of x is exactly what we expected to get. So we just need to follow gradually like that. So I think the key part will be to remember the gamma function identity here. We need to remember that. And we also need to remember that this is cos. So those are like the key parts. So once all of those are in place, then we are good to go. So that was problem 6. Then we'll move on to problem 17. So problem 17. So for problem 17, I want to show that the Mellin transform of e raised power minus x is gamma s, and explain why this leads to a major G representation. Okay, so solution, we need to know that the Mellin transform of a function f of x is defined by some special m, actually, mf of s equals integral from 0 to infinity x raised power s minus 1 f of x dx. Then we can let f of x to be equal to e raised power minus x. So if f of x is e raised power minus x, then we say that m e raised power minus x s of s is integral from 0 to infinity x raised power s minus 1 e raised power minus x dx. But this integral is precisely a definition of gamma function. So it is the definition of the gamma function. Okay, being the definition of the gamma function, we see that that's a gamma s, which is equal to integral from 0 to infinity x raised power s minus 1 e raised power minus x dx. So that goes without saying, right? So we can say, therefore, the Mellin transform of e raised power minus x of s is simply gamma s. Simply gamma s, like that. So yeah, that simply settles. Okay, do we have some extra thing to prove? Okay, then we need to explain why this leads to a major G representation. Okay, yeah, we still have that part. So, but we have established the fact that we have established that first part, talking about the fact that the Mellin transform of e raised by minus x is gamma s. So that is easy to come by. Then next, we talk about the connection. So the major G function is defined through a Mellin Barnes contour integral involving products of gamma functions. So that's G sub P comma Q M comma super M comma N Z. So you have A1 all comma. So you have A1 comma all the way to A sub P. Then you have B1 comma all the way to B sub Q. And all of that is 1 over 2 pi I integral on across L. And you have phi of S Z raised power S ds. So where phi of S is equal to, you have this multiplication from J equals 1 to M of gamma B sub J minus S, then multiplication multiplication from j equals 1 to m of gamma 1 minus a sub j plus s all over multiplication from j equals m plus 1 to q gamma 1 minus b sub j plus s, then multiplication from j equals n plus 1 to p. Okay, this is actually n here. Then gamma a sub j minus s. Okay, so since the Mellin transform, of e raised to power minus x is already a gamma function. It's already a gamma function. It fits naturally into the Meijer G framework. Okay, indeed, e raised to minus x is actually g sub 0 comma 1 super 1 comma 0 x given minus 0 like this. Thus, Meijer G functions arise naturally whenever Mellin transforms produce gamma function products. And with this, we come to the end of this interesting video talking about the unified theory of special functions. So that's a very interesting thing to look at. Right. So I'll just flash the questions once again while we then you can try your hands on them and see how well you understand the gist. So we have problems 1 to 3, 4 to 8 here. Okay, maybe that was too fast. 4 to 8, 9 to 12, 13 to 16, 13 to 16, 17 to 20. All right, so let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, what exactly would you say you're waiting for? Why not go ahead and subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives some special privileges that you'll see when you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.